Hey guys, I'm Zhenfeng Zhang and this is the time for homework 10. I'm going to do a presentation for the first two questions. Okay, and let's see the first question. We need to find out these 7 processes, collect the definition and the simple properties. Okay, for the first one, it is the Poisson process, and we know that the meaning of Poisson process is that we can get a call from time 0 to time t, and the call number is k, and for this probability mass is this equation, and we know that the mean of this Poisson process is gamma t, is lambda t, and it is clearly that if the t increase and we get phone numbers are increased, so the mean should be increased with t, and also the autocorrelation is equals to lambda square t1 t2 plus lambda times with the minimum of the t1 and t2. And we also know that the variance is lambda t, and it is very useful. And for Poisson increments, and it is interesting that the increment is something special for Poisson impulse, because the Poisson impulse is something like if we got the increments is very little, it's very small, and it is limited to 0. So they are actually the same case. And for the Poisson increment, we have got the random variable yt equals to xt minus xt plus sigma minus with xt, and that is the invert interval of t, and we use this interval to over sigma, and if sigma is nearly equals to 0, and in that case that is actually the Poisson impulse, so they are very similar. And for the increments, we got the probability process is equals to this one, and this just use the Poisson process to calculate. It's easy, and the lambda t is equals to the mean is equals to lambda, and for the autocorrelation is equals to this equation, and we're gonna analyze the difference between if t1 and t2 is less than sigma and t2, which means that it is sigma and t1 and t2 are overlapped, and in this case it is overlapped. And for the Poisson impulse, and that's the differentiate of the Poisson increment. That's the differentiate of the Poisson process, and a special case for Poisson increments. And in that case, in the impulse case, the zt equals to the differentiate function of Poisson process, and the mean is equals to lambda. And so easily we see that autocorrelation function equals to this equation, and it's just a differentiate of the autocorrelation from Poisson process, and it's clear. And in the first case, we're gonna find out the semi-random telegraph, and it is clear that the semi-random telegraph is when k is even in 0 to t, then xt equals to 1, and k is odd in 0 to t, then it's equals to -1. So the probability equals to this equation and this equation, and we use this function. We use these two equations. We're gonna find out the mean equals to e with the power of -2 lambda t, and autocorrelation equals to this equation. And the random telegraph signal is just a special case. It's just a general case for the semi-random telegraph, because the semi-random telegraph means that we know actually when 1 happens and -1 happens, but in random telegraph, we don't know where the 1 and -1 happens. So we put a random variable to the semi-random telegraph. It is that like this. We put an a, which the probability of A equals to 1 minus 1 are both are 1 over 2. And so because it is random, for a very long time it is very clear that the random mean is actually 0. It is obviously. And the autocorrelation, of course, is writing like this. And for the random walk, and it's also a general case for the random telegraph signal, because in random telegraph signal, we use the step is equals to 1, but if the step is not equals to 1, then it is a random walk. So the random walk, we're gonna find out the probability mass is equals to combination with n and n plus r over 2, and with the probability we choose the s instead of the minus s. So actually the mean is equals to 0, and because it is also a general case for the random telegraph signal, and the autocorrelation is equals to the minus from n and m. It is the different time and to time with s squared. And in the Wiener process, and it is also called a Brown motivation, because it is just a special case for the random walk. If we put s is limited to 0 and t is limited to 0, that means that the periodical is very small and the time is very small, but the number from happen about this random walk is large, but the step is also very small, and that is just a case in the physics world. Okay, and that is a limitation. And we know that we have this function. We can write from the lecture notes. We all know that the density function is equals to this one, and this is just like a normal function. And the mean is equals to 0, and the r is also kind of, this equation is just like alpha, because we know that the limited, we must make a definition that the alpha equals the alpha is a constant, and this constant must be exist for the limitation of s squared over t. And that's just the definition about Wiener process. Okay, that is the first question. And in the second question, we wanted to know the definition of this stochastic process. And first one, the Wesson stationary. We notice clearly that the mean should be constant, and autocorrelation should be a function of the interval of t. It's like this. And the independent increment with definition is that the probability from the different of interval of t that is non-overlapping should be independent. We call write like this, and this one is called independent increment. And for the Markov process, we also know Markov process as a memoryless process, which means that the present is not related to the past, and future is not related to the present and past. So we're gonna write like this. Assume that there are many events happened in this time axis, and for T1 it is future, and for T2 it is point to now, and for T3, T4 to Tn, that is past events. So the probability of the future events that depends on the now, the past, is unrelated to the past. So this case is not be calculated. So this function should be equals to the future depends on now. And for the normal process, we're gonna know that for n random variabilities, they should be joint normal for any t, and density function should be a normal function. Writing like this, it is very complicated. And for x equals to this matrix, and the mean is equals to ex, and the autovariance is equals to this one, and this is a transpose. And this is a very complicated case. We're gonna put a mark here. It's complicated. And in the fifth case, the process relationship, this is my, the fifth question, we're gonna find the SSS process, the street sense stationary process. I think I also call this process as a special case for the Y-sense stationary process, and which means that the density function of this joint or random process should not be related with time t, which means that if xt is sxx, and it means that this density function should not related to t, and we're gonna find it is interesting that this is not a process anymore. It is just a random function, random variability density function. See that, and the mean is equals to sigma, and instead of sigma t, and it is a constant. It's not a function. And for this one, it's just related to t1 minus t2. So it's not related to which time moment it is. It's just related to the time interval. And for the autocorrelation, it also should be same with the WSS. And attention here that the E of x squared should be exist. And lastly, for the white noise, definition is that its mean should be 0, and the autocorrelation should be a QT1 times delta T1 minus T2, and which means that the value is maybe different at different times, and they are actually independent because here is a random process QT, and they are uncorrelated. And for the second question about the mean periodic process, which means that we can find, if we know a single time, and we can find all the statistic process of the other time. And for the definition function, we're gonna find this equation, and in this equation we have a definition that if we know the limit of t is nearly to unlimited for this function, for this equation is equals to 0, then this process must be a mean ergodic process. And it is also can write this equation to the covariance. And that's all. Thank you.